Hello everyone. In this class of fluid mechanics, we are going to study about continuity equation. Okay. So in last class, we have discussed about systems and control volume. Right? Like what is system and what is control volume. System basically was of two types, closed and open. So to study open system, we make use of control volume, right? So now, moving further, we will study about continuity equation. But before we get to continuity equation, we need to know a very basic principle that you must have studied. What's it? Conservation of mass. Conservation of mass. Fine. This is the principle from which we will derive the continuity equation. It's a very basic equation used widely in all over the fluid mechanics. Fine. So what's conservation of mass? Let's first talk about system, then we move on to control volume. Let's say this is my system. Fine. Let's say this is my system. So I know this is closed real boundary, right? Closed real boundary, which implies no mass flow. No mass flow. The mass can neither get in, neither the mass can get out, right? There is no change in mass, which means mass of system is constant. Mass of system is constant. This is closed system, right? Or what I can say, that change in mass of system with respect to time is equal to 0. Fine. So this was the law of conservation of mass for closed system. For any closed system, mass of system will remain constant and its rate of change with respect to time is 0. Now let's talk about control volumes, in which we are more interested, right? For the study of subject of fluid mechanics, as we are more concerned with flows now, and most of the flow systems are open systems, right? There are pipelines where we consider the control volume. So we need to know how the conservation of mass principle applies to flow systems, right? Let's see. Like in last class, I am considering pipe. Fine. And let's take some control volume here. Let's say this is my control volume, right? This is my control volume. Now there must be some mass going in, some flow rate going in, and there must be some flow rate going out. In closed system, no mass was flowing in, no mass was flowing out. It was a closed system. But in flow systems or in open systems, some mass can flow in, some mass can flow out. What's another thing that can happen? Mass can also accumulate in control volume, right? Mass can accumulate in control volume. Fine. So let's say I assume here that the mass is getting accumulated in control volume. What's the rate of accumulation of mass? Let's say there is mass is increasing in control volume with time. What's the rate of accumulation? I can write that thing as D of mass of control volume with time. Fine. Rate of change of mass of control volume with respect to time will be equal to what will be the mass accumulation? Mass going in, mass flow rate going in minus mass flow rate going out. Fine. Right. What's happening over here? All the extra mass, let's say there is 10 kg of mass I put in a system and I bring out the 5 kg of mass. What happened to the rest of the 5 kg? It remains inside the system. It's as simple as that. Here I am not talking about exact mass, I am talking about mass flow rate. So if there is a M1 mass flow rate going inside the system and M2 mass flow rate going outside the system, then the rate of accumulation will be equal to M1 minus M2. It's as simple as that. So this was my conservation of mass principle. We have seen it for both. We have seen it for both system as well as control volume. However, in my subject of fluid mechanics, I am more interested about control volumes. So we will see how we will drive, how continuity equation can be derived from this conservation of mass equation. Fine. Let's move on. Yeah. First of all, how can I write a mass flow rate in any flowing system? How can I denote a mass flow rate? Right? Like let's say, like there was a, like let's say assume that the speed here was V. Right? As the fluid is flowing, here the speed is V. And density of fluid is here is rho. Then what will be the mass flow rate? What will be the mass flow rate? It will be equal to rho. Fine. Rho is density. Rho is density multiplied by its velocity multiplied by area, cross-sectional area, this area. Yeah, this area, this cross-sectional area. So this will be my mass flow rate. Now it's not as simple. I will not go into much detail. Here V is actually the average velocity, right? Average velocity. As you know from Newton's law of viscosity, we have discussed earlier. If I say, let's say, this is my pipe. So my velocity profile will not actually be the same, right? It will somewhat be like this. We have discussed it already in the class, right? The velocity near the boundary will be less and it will be the maximum at the center. Fine. In pipe flow, we can derive this by Newton's law of viscosity. Let's leave it till now. Yeah. So what's the velocity? What's the average velocity came out from here? V average that we consider at a cross section here. This one was V average, right? So mass flow rate is equal to rho at that cross section multiplied by its average velocity into that cross sectional area. That is my mass flow rate. Clear? Right? So yeah. So let's move towards the continuity equation. It's a very simple. So let's now, what was the conservation of mass principle? Mass in minus mass out is equal to d of m of control volume divided by dt. Right? So what can I write for m in? Let's say rho 1 a1 v1, right? Minus rho 2 A2 V2. Fine. It will be equal to delta M CV, that is change in mass of control volume. So this is my mass flow rate going in, this is my mass flow rate going out, this is my rate of change of mass of control volume. Fine. Now for steady flow systems, as I have told you yesterday also in last class, that mostly we are going to study about steady flow systems, right? What happens in steady flow system? The properties of fluid or my data does not change with time. Does not change with time. So I can say in steady flow systems, delta MCV will be equal to 0, or I can say that mass of control volume will remain same. Fine. Which also implies that mass going inside will be equal to mass going outside of my system. Mass going inside will be equal to mass going outside. How? As my M in minus M out was equal to d of mass of control volume by dt. Now this thing is 0. Why? Because of steady flow, right? Because of steady flow, this thing tends to 0. So my mass in becomes equal to mass out, right? Or I can say rho 1 A1 V1 is equal to rho 2 A2 V2. Fine. So if my flow is incompressible, now let's say, so basically this is my continuity equation. This is my continuity equation. Keep in mind here we have assumed one thing. What's the assumption here? Assumption is steady flow. Assumption is steady flow. Otherwise this equation is not valid. This equation is valid only for steady flow. Fine. So keep that in mind. If you are solving any numericals further in your studies, so only if the flow is steady, only then you can use this continuity equation. Otherwise there will be one more element that will came into picture. What's that? Rate of change of mass in control volume. We have put that to 0 in this case. Fine. So now let's say, now assume further one thing. Let's say flow is incompressible. Let's say flow is incompressible. So if my flow is incompressible, it implies that rho 1 will be equal to rho 2, right? So I can further simplify my equation to A1 V1 is equal to A2 V2. This is also a continuity equation. Continuity equation. However, here I have two assumptions, right? First one is the initial one, that the flow is steady flow, and second one here is it's incompressible, right? It's incompressible flow. Fine. This is my basic assumption over here. Yeah. So this was my continuity equation. It was a very simple equation. Actually, it is used very widely all over the fluid mechanics. Next, as many miracles we are going to see, we will make use of Bernoulli's equation, and we will see the applications of Bernoulli's equation, and everywhere the continuity equation will come into picture. It's very useful. Fine. I know it's very basic, it's very simple, but yeah, it's very important concept. That's why I discussed in this lecture. I hope you are very clear with the continuity equation. If you have any doubt, okay, or any suggestion or whatever, you can tell me in comments. Please do share share, like, subscribe the channel.